All right, let's dive straight into this explainer. We're doing a total high-impact flash revision session today, specifically targeting the D and F block elements. If you're gearing up for NEAT, you already know maximizing your chemistry score is all about zeroing in on those high-yield patterns. So we're taking what usually takes, a solid 30 minutes to review, and we are condensing it into under 10 minutes of pure exam-tested facts.
Here's our flash revision syllabus for today. We're hitting the NEAT setup, cracking configurations, the secrets of ion colors, mastering magnetic moments, KMNO4 and oxidation states, and finally, some essential exam hacks. Let's get to it.
Starting off with Section 1, the NEAT setup. We literally have to start here to validate the stakes. This specific chapter consistently guarantees 2 to 3 questions on every single NEAT paper over the last decade. Honestly, it's an absolute goldmine. Unlike other chapters where the question count just completely fluctuates year to year, the D and F block reliably delivers. So treating this lightly, no serious aspirant can afford to do that. The questions usually split super predictably, right down the middle, half factual recall, half concept application. To master this efficiently, you really need a meta strategy. Don't just passively read the textbook. Follow these exact steps to condense all that chaos into a single high-yield fact sheet. First up, take one dedicated day to build this sheet. Second, group your practice questions by specific subtopics. Schedule 15-minute daily bursts to solve them instead of blindly taking full yearly papers. This is going to help you spot exactly how examiners frame their questions. And finally, prioritize the heavily tested areas, which actually is exactly what we're covering right now. Moving on to Section 2, cracking electronic configurations. Now, what's genuinely interesting about this first technical hurdle is how predictably examiners try to trip you up. The D block has 2 major rule breakers in the 3D series. Just remember our mnemonic here. Crazy customers want half or full D. That stands for chromium and copper. Since half-filled and fully filled subshells offer a ton of extra stability, they actually just borrow an s electron. So chromium isn't 3d4 4s2. It grabs an electron to become the highly stable 3d5 4s1. Copper does the exact same thing to hit 3d10 4s1. Lock that memory 8 away, it's a total lifesaver. And this brilliantly sets up the absolute ultimate shortcut for ion configurations. A massive trap, I mean literally a huge trap students fall into, is ripping electrons out of the d orbital first. Always remember, when a transition metal forms an ion, those outer s electrons leave first before you even think about touching the d electrons. Take iron 2+, for instance. You remove the 4s electrons, leaving it purely as 3d6. Stick to this one rule and you'll fix 90% of your configuration errors.
All right, Section 3, the secrets of ion colors.
Let's figure out why these transition elements are so famously colorful. It all boils down to a d-d transition. Think of the d orbitals splitting into a lower and an upper staircase. If there's an unpaired electron sitting on the bottom step, a photon of visible light comes along and provides just enough energy to kick that electron up to a higher step. When it absorbs a specific wavelength to make that jump, the color we actually see is the exact complement of what was absorbed. It's like a chemical splash of color. Now, to save yourself massive amounts of time on multi-correct exam questions, here's a huge hack. Always scan for colorless D0 and D10 ions first, and just instantly eliminate them. If an ion is D0, say scandium 3+, it has 0 electrons to promote. If it's D10, like copper 1+, every single orbital is completely stuffed full, so there's nowhere for an electron to jump to. Spot these on a color matching question? Boom, cross them out immediately. And please, please don't fall into the trap of thinking zinc has no d electrons, and that's why it's colorless. Actually, zinc 2+ has 10 d electrons. The real deal is that they are all perfectly paired up. The subshell is completely full. Think of it like a fully booked hotel. There are absolutely 0 vacancies left to allow for those colorful d-d electron jumps. Next up in our playbook, Section 4, Mastering Magnetic Moments. We are locking down guaranteed marks here. By rigidly following this 3-step calculation strategy, you will never stumble on a magnetic moment question again. First, figure out your ion's configuration and place those d electrons using Hund's rule. Fill the orbitals singly before you start pairing them up. Count the unpaired electrons. That is your n value. Second, just plug n into the spin-only formula. It's the square root of n times n+2. So let's take chromium 3+, for example. It has 3 unpaired electrons. Plug it in, 3 times 5 is 15. The square root of 15 is 3.87 Bohr magnetons. Honestly, just build a quick mental lookup table for the square roots of 3, 8, 15, 24, and 35, and you will totally blaze through these questions on exam day. Entering the boss battle phase. Section 5. KMNO4 and oxidation states. Potassium permanganate is this incredibly powerful oxidizing agent, but its behavior totally morphs depending on its environment. You need to burn this summary checklist into your memory right now, because these specific medium-dependent reduction products show up almost every other year. In an acidic medium, it reduces down to a totally colorless manganese 2+ ion. Shift to a neutral or slightly alkaline medium, and you get a brown precipitate of manganese dioxide, which is Mn+4. And in a strongly alkaline medium, it forms the bright green manganate ion, Mn+6. While we're on the topic of extremes, let's contrast the fluff block elements for a second. Remember that both lanthanoids and actinoids share a base +3 oxidation state. But the actinoids, they are highly radioactive and way more complex because their 5f, 6d, and 7s valence electrons have super similar energies. To remember just how high their variable states can go, use the mnemonic never put off for neptunium and plutonium. Reflecting that energetic shell, they can stretch their oxidation states all the way up to a massive +7. Time for Victory Lap, Section 6, Essential Exam Hacks. Look, you simply cannot walk into this exam without locking down the lanthanoid contraction. Here's the deal. As you move across the lanthanoid series, you're adding protons to the nucleus, right? And the new electrons are dropping into that inner 4f orbital. But here is the catch. Those deeply buried 4f electrons do a completely terrible job of shielding the outer electrons from the growing pull of the nucleus. Because of this incredibly poor shielding, the increasing nuclear charge literally just pulls the entire electron cloud tightly inward. The result? A steady, relentless decrease in atomic size. But just knowing the definition, yeah, that isn't enough. You have to memorize these 3 core exam consequences. First, because of this contraction, the 4d and 5d metals end up having nearly identical radii. The classic NEET example they love to use is zirconium and hafnium, almost the exact same size. Second, since all the lanthanoids are so incredibly similar in size, separating them chemically becomes a total nightmare. And third, as they shrink across the series, their positive charge density spikes, meaning the basic character of their oxides steadily decreases. All right, we've covered the absolute highest yield patterns to make your revision as efficient as possible. But I want to leave you with a bit of a provocative thought to really test your deep understanding. We know zinc is colorless because it has a full D10 shell, no DD transitions allowed, right? So if the manganese in potassium permanganate is in a +7 oxidation state, meaning it has completely emptied its d orbitals to a D0 configuration, how on earth is KMNO4 so intensely, famously purple? What hidden chemical phenomenon is causing that color if it is definitely not a DD transition? Here's a hint. It involves the transfer of charge between the oxygen and the metal. Look up the exact mechanism. If you can confidently answer that, you, my friend, are truly ready for exam day. Thanks for joining this explainer and absolutely crush your revision.